In question 5, we have a fixed mass of ideal gas at a low temperature in a container at a constant pressure. The gas is heated and the volume of the container changes, so the pressure stays at 1.00 times 10 to the 5 pascals. At 0 degrees C, the volume is 2.20 times 10 to the minus 3 cubic meters. We need to add a graph to these axes to show how the volume of the gas varies with temperature in degrees C. Well, we're given a point here. At 0 degrees C, the gas has 2.20 times 10 to the minus 3 cubic meters, and at minus 273 degrees C, absolute zero, the gas will have zero volume. We also know that pressure times volume is equal to the number of moles times the molar gas constant times the Kelvin temperature, and so if the amount and pressure are constant, the volume is directly proportional to the Kelvin temperature. So we'll get a straight line like this. In B, we need to find the number of moles of gas present in the container. Well, again using this formula, rearranging for the number of moles, putting in the values, the molar gas constant is given in the formula sheet, and we must use the Kelvin temperature. We get 0.0970 moles. In C, we need to find the average kinetic energy of a molecule when the gas is at 50 degrees C, giving our answer to an appropriate number of significant figures. Well, for this, the kinetic energy is equal to 3 times the Boltzmann constant times the Kelvin temperature over 2. Putting in the values, 50 degrees C being 323 Kelvin, gives a kinetic energy of 6.69 times 10 to the minus 21 joules. In D, we need to find the total internal energy of the gas at 50 degrees C. Well, this is the kinetic energy of a molecule multiplied by the number of molecules. We had 0.0970 moles, and multiplying by the Avogadro number gives the number of particles. This gives an internal energy of 390 joules. In E, by considering the motion of the molecules, we need to explain how a gas exerts a pressure and why the volume must change if the pressure is to remain constant as the temperature rises. Well, the particles collide with the walls of the container, so changing direction. This involves a change in momentum, so a force must be exerted on the particles. In E, by considering the motion of the molecules, we need to explain how a gas exerts a pressure and why the volume of the container must change if the pressure is to remain constant as the temperature rises. Well, the particles collide with the walls of the container, so changing direction. This involves a change in momentum, so a force must be exerted on the particles, as through Newton's second law, force equals rate of change of momentum. The particles exert a force of equal magnitude in opposite direction on the walls, due to Newton's third law. This force produces the pressure, as pressure is equal to force divided by area. As the temperature rises, the particles travel faster, so on average the collisions are harder, so producing a greater force due to a greater change in momentum. If the container increases in size, there will be a longer to travel between the collisions with the walls, and therefore there will be fewer collisions per second. This will balance the effect of the harder collisions, so maintaining a constant pressure.